The scene unfolding today in Haifa has become one of the most talked about events, not only across Israel, but also throughout the international media cycle. A bridge in the city collapsed following the impact of what officials are describing as a stray Iranian missile. The event has generated immediate concerns about urban safety, infrastructure resilience, and the broader implications of cross-regional conflicts spilling into civilian centers. To really understand what happened, we have to dive into the structural aspects of the bridge itself, the destructive power of the projectile, and the way Israel's defense systems function in scenarios where urban areas become the accidental front line. Haifa is known for its combination of modern infrastructure and its role as a key industrial and strategic hub. The bridge in question was a vital connector for daily commuters, freight transport, and emergency response routes. It was designed with reinforced concrete, steel supports, and seismic safety measures, reflecting Israel's consistent adherence to high construction standards and earthquake-prone zones. However, missile impacts introduce an entirely different category of stress. Unlike seismic tremors that distribute energy across the structure, a high-velocity projectile creates a concentrated point of shock and heat. This bridge, which had been in service for over 2 decades, had undergone regular maintenance, but it was not engineered to resist the direct hit of advanced military weaponry. The missile that struck Haifa was reportedly not guided specifically toward the bridge. Sources indicate it may have been one of the projectiles launched in a broader offensive, veering off course due to interception attempts or navigational errors. Even when a missile is classified as stray, the destructive output remains immense. Depending on the warhead size, the blast radius could reach several dozen meters, and in this case, witnesses described a thunderous explosion followed by the instant collapse of one major span of the bridge. Vehicles present on the structure at that moment were thrown into chaos, with some plunging into the wreckage and others narrowly escaping the collapse. First responders arrived within minutes, dealing simultaneously with fire, debris, and the urgent task of saving civilians trapped under the concrete slabs. From a technical perspective, this event highlights a critical vulnerability in modern cities exposed to conflict zones. Israel, Iron Dome, and David S. Sling defense systems are built to intercept short to medium-range threats. These systems boast interception rates of 85 to 90% under optimal conditions, but no shield is perfect. A missile traveling at high speed can sometimes slip through, especially when multiple launchers occur simultaneously to overwhelm defense grids. The bridge collapse is a stark example of how even one successful strike can disrupt infrastructure, trigger panic, and inflict symbolic damage alongside physical destruction. Examining the performance of the bridge before impact, engineers note that it had passed all recent inspections. The load-bearing capacity exceeded daily traffic demands by nearly 30%. And the structure incorporated redundancy and support beams to prolong durability in case of localized failures. But the energy transfer from a missile strike is unlike any civilian load. At impact, the blast's kinetic energy concentrated on a single support column, instantly destabilizing the load path and causing a cascading collapse. Reinforced concrete can resist compressive forces and steel handles tension well, but neither was sufficient against the extreme thermal and kinetic shock produced in this strike. The aftermath shows twisted rebar, pulverized roadbed, and support columns fractured cleanly at the base, an indication of overpressurization rather than gradual structural fatigue. For everyday viewers, the collapse of the bridge is more than a technical failure. It is a chilling reminder of how modern conflict blurs the line between military and civilian spheres. Bridges are not only practical assets, but also symbolic links that represent connection, resilience, and mobility. In a city like Haifa, where daily life depends heavily on interconnected transport routes, losing one of these arteries disrupts everything from morning commutes to emergency logistics. This impact cannot be measured only in repair costs, but also in the disruption to human life and the psychological toll on residents who now face the reality that critical infrastructure is at risk. Israel's response teams displayed rapid coordination, which deserves attention as a unique point of strength in this crisis. Within half an hour, military engineers, fire brigades, and medical units had secured the site. Drone surveillance was deployed to assess secondary damage and ensure no additional explosives remained. Temporary traffic redirection protocols were enacted almost instantly, showcasing the country's readiness for emergency continuity. The broader design of Israel's national response system is structured around scenarios like this, with pre-planned strategies to absorb shocks and minimize chaos. This capacity for quick adaptation is a distinctive feature that often goes unnoticed. Until crises like today reveal its importance when we evaluate the unique selling points of Israel's infrastructure, planning, and defense strategy. Resilience stands out. The nation builds redundancies, not just in defense, but also in civil engineering. Even with one major bridge gone, parallel routes and alternate pathways limit the scale of disruption. However, resilience does not equate to invulnerability, and this event highlights the constant challenge of adapting to evolving threats. Missile technology continues to advance, with improved accuracy, longer ranges, and higher destructive power. A stray missile striking a bridge raises serious questions about what would happen if future projectiles were intentionally aimed at critical transport hubs, power stations, or desalination plants in coastal cities like Haifa at the international level. Today's collapse has already begun to shape conversations about escalation and deterrence. For Iran, even an unintended strike in a civilian-heavy zone heightens the diplomatic stakes. For Israel, it sharpens the argument for expanding both offensive and defensive measures. Globally, the incident underscores the vulnerability of urban centers worldwide. Cities in Europe, Asia, or North America, though not currently under missile fire, share similar infrastructure designs, which means lessons from Haifa are broadly relevant. Civil engineers may start to consider how bridges and other structures could incorporate blast-resistant design principles without sacrificing efficiency or affordability. In fact, countries that face regular security threats, such as South Korea or Ukraine, might look closely at this collapse as a case study in structural resilience under conflict stress, looking into the design elements of the bridge before destruction. We see a structure that reflected efficiency and modern aesthetics. Smooth gradient curves ensured traffic could flow without abrupt inclines. Wide lanes accommodated both private vehicles and cargo trucks, and reinforced barriers added safety margins. Pedestrian pathways lined one side, serving as a connector not only for cars but also for local foot traffic. Its placement in Haifa was strategic, easing congestion from the port toward industrial zones. These design strengths made the bridge not just functional but also integral to the city's rhythm. Losing such an asset is not only about rebuilding concrete and steel, but also about regaining a piece of the city's identity. Technologically, Israel's capacity to rebuild is advanced. Using modular construction techniques and prefabricated components, new spans can be erected in record time. This efficiency is one of the unique strengths of Israeli infrastructure planning, allowing damaged areas to be restored faster than in many other countries. Moreover, the use of smart sensors embedded in newer bridges provides real-time feedback on structural health, helping engineers monitor stress points and fatigue. While the collapsed bridge predates many of these technologies, the rebuilding process is expected to incorporate them, setting a higher bar for future safety. The fusion of civil engineering with digital monitoring systems is one of the most important performance aspects shaping modern infrastructure resilience. As media coverage amplifies the event, public perception plays a role too. Citizens in Haifa and across Israel are grappling with a dual narrative. Pride in the rapid emergency response and concern about the fact that such vulnerabilities exist in the first place. This dynamic is central to understanding how infrastructure events affect morale. The bridge collapse is not only a matter of steel and stone, but also a blow to the sense of security that everyday routines provide. The question becomes whether the state and its engineers can reassure the population that lessons have been learned, and that future designs will be even more resistant to unforeseen shocks. In summary, the collapse of the Haifa Bridge due to a stray Iranian missile is a convergence of structural science, military conflict, and urban resilience. The bridge itself, a symbol of connection, could not withstand the focused destructive energy of a missile impact. Yet, the rapid response, the built-in redundancies of Israel's urban planning, and the potential for smarter, stronger rebuilding demonstrate both the vulnerability and the adaptability of modern infrastructure. This event forces policymakers, engineers, and citizens alike to confront the reality that in today's world, even civilian infrastructure can become collateral in conflicts that stretch far beyond national borders.